Welcome to the 20th lecture of course Polymer Science and Technology. Today we will discuss the kinetics of the chain polymerization reaction. Polymerization reaction is initiated by initiators. Initiators may be peroxide, hydroperoxide, azo compound for low temperature reactions, redox initiator for room temperature and aqueous system, and photo initiators for light and UV light up to 250 nanometer wavelength. So these are the initiators that can be used to initiate the polymerization reaction in case of chain polymerization reaction. Okay. Now let's see the kinetics of chain polymerization reaction. Here initiator I. This initiator may be anything: peroxide, hydroperoxide, azo, redox or photoinitiator. So this initiator I will undergo thermal decomposition when it will be exposed to the temperature above its decomposition temperature, and free radicals will be formed. So one initiator is going to form two free radicals. This dot represents the free radical site. Okay, so this step is known as radical generation step. Now this free radical is very active and it can combine with any molecule, especially the monomers. Vinyl monomers basically have a double bond between carbon-carbon, and out of these two bonds, one bond is the pi bond, another bond is the sigma bond, and you know the sigma bonds are much stronger as compared to pi bond. So this free radical will basically attack to the pi bond of the vinyl monomers. Okay, and once it will attack the pi bond, what will happen? It will combine with the first carbon atom, and the free radical site means the lone electron will be shifted to asymmetric carbon atom here. So the free radical site of the initiator or the free radical after the reaction with the monomer will shift to asymmetric carbon atom, and this step is known as the initiation step. Now this whole species will, you can say that now this is another second free radical. The basic or the initial free radical was the R free radical, but once it will combine with the first monomeric unit, then entire structure will be a free radical, and this entire free radical may attack to another monomer, and it will attack on the pi bond of another monomer, and that monomer will also be attached to this structure, and the whole, now this whole is the free radical. Now this free radical is having basically two monomeric unit, and the free radical site will shift from the asymmetric carbon atom of the first unit to the asymmetric carbon atom of the second unit. So likewise this free radical site will keep on jumping from one monomer site to another monomer site, and monomers will keep on attaching to this growing polymer chain in every propagation step. Okay, and this propagation step, as I told you earlier in the previous unit, that it may be head to tail type or head to head type. So there are different permutation combination how the incoming monomer unit will get attached to the growing polymer chain. So after propagation, the third step is the termination step. In termination step, two growing polymer chain, let's say this is my first growing polymer chain which is having one free radical site, and this is another growing polymer chain, the free radical site is also present here. Now these two free radical site, or you can say the lone electrons may combine to form the bond between these two carbon. Okay, so you can see here this bond is formed between two growing polymer chain, and this is a kind of a coupling. This first chain may get coupled to the second chain, and this type of reaction or termination reaction is known as termination by coupling, in which two growing polymer chains will just get coupled with each other, and the final polymer chain will be having molecular weight equal to the molecular weight of these two individual chains. In second type of termination is termination by disproportionation, in which one of the growing polymer chain, let's say this left hand side chain, will give one hydrogen atom to another chain to the right hand side. So here it will be CH2 on the symmetric carbon atom. Now the valency of this asymmetric carbon atom is satisfied. One bond here, two hydrogen here, and one bond here. So there are four bonds, so the valency gets satisfied, and this growing polymer chain will be, now it will be a dead polymer chain. And once it will give one hydrogen from symmetric carbon atom, so here a double bond will be developed between the symmetric and asymmetric carbon atom. So how we can distinguish between mode of termination, either by coupling or disproportionation? If double bond are present in the structure, then we can say termination is by disproportionation. And why do we call it disproportionation? Because there is a disproportion of one hydrogen atom between these two chains. Means my left hand side chain will donate one hydrogen atom to my right hand side chain. Correct? So in right hand side there is one extra hydrogen atom, and there is lacking of one hydrogen atom. So this is the disproportionation. I think we have discussed all this in previous unit. Now this is time to look at the kinetics. So again, starting from initiator, I is going to decompose into two free radical, and the rate of the reaction, this is irreversible reaction. Rate of reaction is Kd, which is decomposition. D stand for decomposition. Then initiation stand for this R dot plus M irreversible reaction Ki, where Ki is the rate constant for initiation rate constant, and this M1 dot is the first species formed during the initiation polymerization. Then M1 dot is going to react with another monomer M, and likewise this whole species M2 dot will again react with another monomer, and it will form M3 dot, and M3 will react with another monomer, it will form M4. Likewise this will continue, and we can write it in a generalized term, Mx dot plus M will give me the Mx plus 1 dot. Okay. So this whole is the propagation step. There are n number of propagation steps in chain polymerization reaction. Now two growing polymer chain, Mx dot and My dot, they may be terminated either by coupling or by disproportionation. If they are going to be terminated by coupling, it will be Mx plus Y, or by disproportionation it will be Mx plus My. So these are the two modes of the termination. Okay. Now rate of monomer disappearance, that is the rate of polymerization, is given by minus dm by dt equal to Ri plus Rp. where Ri is the rate of initiation and Rp is the rate of propagation reaction. Number of monomer reacting in initiation step is far less than the number of monomer reacting in propagation reaction. Therefore, we can easily ignore this Ri part. Therefore, the rate of monomer disappearance is almost equal to rate of propagation step. In other words, we can say Rp, where this Rp stands for rate of polymerization or rate of propagation, is equal to rate of monomer disappearance is equal to Kp m dot m. Here Kp is my rate constant for propagation reaction and m dot m, these are the reactant for the propagation reaction. So it will be Kp concentration of m dot and concentration of m, where concentration m is the concentration of the monomer and concentration m dot is the concentration of all chain radicals. All chain radicals mean m1 dot and larger, that's mean m1 dot, m2 dot, m3 dot, m4 dot, likewise mx dot. Okay. It is difficult to measure the concentration of the radical since concentration of m dot is very low. It is of the order of 10 to power minus 8 molar. Therefore, a steady state assumption has been made, and according to this assumption, the concentration of radical increases initially. Why? Because initiator will decompose, so the concentration of free radicals will increase initially during the polymerization, but almost instantaneously reaches a constant steady state value. Okay. According to the above assumption, Ri is equal to Rt. That means rate of initiation is equal to rate of termination. So steady state will be achieved only when the number of free radical getting initiated and the or we can say rate of free radical initiated is equal to rate of free radicals terminated. Then only the concentration of the free radical will attain steady state value. So this is the basic assumption where Ri is equal to Rt according to steady state assumption, and Rt we can see from the above mechanism that Rt is equal to 2 kT m dot square, because in my termination reaction 2 m dot, mx dot and my dot, they are representing 2 m dot here, 2 m dot square. So it will be 2 kT m dot square, and this factor of the 2, use of factor of 2 in termination equation follows generally employed for reaction creating or destroying radicals in pair. So as we have seen that the free radicals will be formed in pair and free radicals will be destroyed during termination reaction in pair. So the factor of 2 has been employed here. Okay. So rate of initiation Ri will be equal to rate of termination. But again here the concentration of m dot is difficult to measure. So what we can do, from here we can separate out the concentration of m dot is equal to Ri over 2 kT under root out to the power half. Substituting equation 2 in equation 1, this is my equation 1. So in equation 1 I can put the value of m dot. So rate of polymerization or rate of propagation Rp is equal to Kp times Ri 2 Kt under root times m, concentration m. So rate of producing primary radical, the rate of producing primary radical Rd is equal to 2f Kdi, where I is the concentration of initiator and Kd is the rate of decomposition of initiator, and the factor 2 is used here because the initiator free radicals are formed by the initiator in the pair, so the factor of 2 is used, and F is the efficiency factor. That's mean that not all the initiator molecules are going to form free radicals. If F, the value of F is 0.9, means that the 90% of initiator molecule will form free radical R. So primary radicals means R dot, and secondary radicals mean any form of M dots, M1, M1 dot, M2 dot, M3 dot, likewise. So primary radicals are immediately utilized for initiation reaction. Therefore Ri is equal to 2FKDI concentration, because all the initiator that has formed the free radical R will be immediately used to start the initiation reaction. That means rate of initiation is equal to the rate of initiation formation in radical formation step. Okay. Now replace the value of Ri in equation 3 from equation 4. In equation 3 we will put this value from equation 4. So here it is Ri. Now instead of Ri we will put 2FKDI concentration. So my rate of polymerization will become Kp 2FKD concentration I over 2 times Kt to the power half times concentration M. So here 2 will get cancelled out, and the final equation for chain polymerization reaction, rate of polymerization or rate of propagation reaction is equal to Kp, where Kp is the rate of propagation reaction times concentration M, the concentration of the monomer, under root FKDI over Kt, where Kd is the decomposition rate constant and Kt is the termination rate constant, and concentration I is the concentration of the initiator taken at the time of reaction. So from this equation what we can conclude that the rate of polymerization Rp is directly proportional to the concentration of the monomer. That's mean higher the concentration of the monomer, greater will be the rate of polymerization. Also the rate of polymerization is proportional to under root of initiator concentration. That's mean if we are going to double the concentration of initiator, it doesn't mean the rate of polymerization is going to be doubled, because Rp is proportional to the under root of concentration I. It will increase only according to under root times of concentration. Okay. So this is the end of 20th lecture. I hope you have understood. If you haven't understood some having some problem, we can discuss this in the class interaction. Okay. So thank you very much for your patient hearing.